So, let's talk about something huge. Our planet is warming up, and man, is it happening fast. In this explainer, we're going to look at what the science says is driving this change, how Earth's natural systems are trying to keep up, and what a potential path back to stability actually looks like. Okay, let's jump right in.
Okay, so first things first, we've got to talk about speed. The planet definitely has its own natural cycles. Things like coming out of the Little Ice Age. But those are slow, gradual changes happening over many centuries. What we've seen since the Industrial Revolution, that is something else entirely. A 1.5 degrees Celsius jump in just 200 years. That's not some gentle, natural rhythm. No way. That's a spike, a vertical line on a graph just shooting straight up.
All right, so if this isn't just nature doing its thing, then what is it? How can we be so sure about the cause? Well, it turns out scientists have found what you could call a human fingerprint all over this recent warming.
And it really all boils down to this one core concept, the greenhouse effect. It's a good thing, normally. Certain gases in our atmosphere act like a natural blanket, trapping just enough of the sun's heat to make our planet livable. But what we've been doing by burning fossil fuels is basically just throwing another blanket on, and another, and that's trapping a whole lot more heat.
And you know what? We can literally watch this happen in the data. This is the famous Keeling curve. For ages, for centuries before we started building factories and driving cars, CO2 levels just hummed along right around 280 parts per million. Stable. But just look at what's happened since. That line has gone almost completely vertical, on track to hit 427 parts per million. That acceleration? That's the story right there.
So here's where we are, 427 parts per million. And let's be super clear about this. The last time our planet's atmosphere had this much CO2 in it was at least 800,000 years ago. This isn't just some small fluctuation. It's a massive, massive departure from the world humans have always known.
Okay, but the big question, right? How do we know that extra CO2 is our fault? It's actually pretty clever. Think of it like a chemical fingerprint. Carbon from, say, a breathing forest has one kind of signature. But carbon from fossil fuels, stuff that's been buried for millions of years, has a totally different old signature. And guess what? As this quote explains, scientists can see a flood of that old carbon in the atmosphere. It's the smoking gun.
And the sheer scale of this, just mind-boggling. Every single year, we're pumping 42 times gigatons. That's 42 billion tons of CO2 into the air. A single gigaton, by the way, weighs about the same as 200 million elephants. And the grand total since this all started, a whopping 1,900 gigatons. So you might be thinking, hang on, if we're trapping that much heat, why isn't it 1 billion degrees outside? And that's a great question. The reason is that our planet has its own incredible defense mechanisms, or buffers, and they have been working overtime to protect us.
And here are our two heroes, the oceans and ice. You can think of them as the planet's giant heat sponges. They are doing the heavy lifting, soaking up almost all of this extra energy. So the warming we actually feel, that's just the leftover heat that these two massive systems haven't been able to absorb yet.
And this really puts it in perspective. Just look at how much work the oceans are doing. That huge slice shows that the ocean has soaked up over 90% of all the extra heat we've generated. That tiny little sliver for the atmosphere, that's what we're all so worried about. It really shows you that what we're experiencing is literally just the tip of the iceberg.
And that brings us to our other big buffer, ice. Ice is, it's like a superhero when it comes to absorbing heat. Get this, it takes 80 times more energy just to melt ice than it does to raise the temperature of the water that comes from it. It just soaks up heat like crazy without the temperature budging, right up until the moment it's gone.
And that right there is the million-dollar question. Or maybe the trillion-dollar question. These buffers are protecting us, for now, but they're not bottomless. What happens when the ice is gone? What happens when these buffers are full?
Well, the scary part is we don't really have to guess. Our planet's own history book has a chapter on this, and honestly, it's a pretty stark warning about what a world without those buffers looks like. Yeah, if you want to know what a world without ice looks like, we just have to rewind the tape. Geologists have found that our planet has gone through really long periods where there was no ice at the poles at all. And let me tell you, it was a totally, fundamentally different planet. So back then, in those ice-free times, the global average temperature wasn't just, a little bit toastier. We're talking 5 to 6 degrees Celsius hotter than it is today. That is a massive shift in the planet's entire energy system.
And the result of all that extra heat and no ice? Sea levels. They were 240 feet higher. I mean, just pause and think about that for a second. 240 feet. Imagine what that does to every coastal city we know today. And remember, this isn't some computer simulation. This is what the geologic record tells us really happened.
And look, we're already seeing the warning lights flash on the dashboard. This extra energy that's trapped in our system is powering more intense storms, more widespread floods, bigger wildfires, and that slow, steady march of sea level rise. These aren't random events. They're the symptoms of a system that's getting overloaded.
Okay, so that warning from the past it's pretty heavy. But the science isn't just about doom and gloom. It actually points to a way out of this, a clear path to get things back on track.
It really comes down to a three-step plan. Step 1, and this is the big one, we have to stop putting more CO2 into the atmosphere. That means phasing out fossil fuels. Step 2, fill that energy gap with renewables, right? Solar, wind, the whole shebang. And step 3, we need to start cleaning up the mess we've already made, actually pulling that excess CO2 back out of the atmosphere and oceans and storing it somewhere safe for the long haul. Because the end game here, the whole point of all this, is to get that CO2 number, that 427, back down, way down, back into a range that we know is safe and stable for human civilization to thrive in.
So, there you have it. We've walked through the evidence, we've seen how our planet's natural defenses are getting strained, and we've laid out a pretty clear three-step game plan. The science seems pretty clear on the what and the how, which leaves us with maybe the most important question of all. What do you think is the single biggest obstacle, not a scientific one, but a human one, to actually making this happen?